Today we're going to get into the details of how molecules form, how covalent bonding works. All the action in chemical bonding, whether it's covalent bonding or ionic bonding, really involves not any electrons, but only the electrons that are closest to the outside of the atom. We haven't talked much about the structure of the atom, but some of the atoms are closer in, and they really don't participate in any chemical action. The ones that are outside can be shared, can be lost, can be gained to change the atom, and that usually results in more stable substances, compounds. There's a name for these electrons that are farthest to the outside of the atom, and that name is valence electrons. So we're going to talk a lot about valence electrons. We don't know that much about the structure in this class of the atom, but the valence electrons are the ones that are on the farthest outside the atom. Since you don't know that much about the structure of the atom, you might ask yourself, how am I supposed to know which electrons are the valence electrons? Or how many valence electrons even are there? Well, the good news is the question, how many valence electrons are there, is easily answered by looking at the periodic table. Whatever the group number is for the representative elements, this means the first two columns and the last six columns of the periodic table, that's the number of valence electrons. The group number is the number of valence electrons. We're mostly going to concern ourselves only with the representative elements, at least for now, because mostly the things that do covalent bonding are representative elements. So here are the representative columns. Column number 1, column number 2, and then column 3, 4, 5, 6, 7, and 8. We're going by the Roman numerals here. The numbers below there go 1 through 18, but that numbering system isn't that useful in chemistry. Really, this is column 1, this is 2, 3, 4, 5, 6, 7, and 8. That's a good way to think about these things. And whatever column it's in, that's how many valence electrons it has. There's a chemist, G.N. Lewis, first American chemist that really amounted to anything. He was an organic chemist. He was mostly concerned with the chemistry of carbon-containing compounds. And what he did was he developed a way of representing the electrons that are involved in bonding. And you can do this with one atom. It's called Lewis dot notation, and that's what we're going to look at now. But then you can do it for multiple atoms that are grouped together in a molecule, and that's called Lewis structures, and we'll look at that a little bit later on today. Now, there are 8 representative groups, groups 1 through 8. So the most valence electrons you could ever have on any atom would be 8. So there's a way of thinking about this that's quite helpful. Think about the symbol of any element, like C for carbon or H for hydrogen. I'm using X here to be sort of generic. If you think about this symbol as having 4 sides to it, and there being a maximum of 8 electrons, Lewis said, why don't we do this? Let's make 2 spots where electrons could go on each side, and we'll represent the dots as electrons. So every dot is an electron. So each side gets a maximum of 2 dots. There are 4 sides around the symbol. That gives you a maximum of 8 dots. So here's how you draw Lewis dot notation for any element. First, write the symbol for the element. Like, I'm going to do boron, so I write a B down. The next thing you want to do is think about this as having 4 sides. You add 1 dot to each of the sides until all the valence electrons are accounted for, or until you run out of sides. So for boron, if I think about boron's position on the periodic table, look it up and you find out it's in column number 3. So that means it should have 3 dots. So I put 1 on one side, switch to a different side, put a second dot there, switch to a third side and put a dot there, and that's all the dots I need. And then the next step is, if you need to, add a second dot to each side until all the valence electrons are accounted for. So let's say I was going to do phosphorus. Phosphorus is in column 5, so I'm going to need 5 dots because it has 5 valence electrons. So I put 1 on one side, switch to another side, third side, fourth side, still don't have enough dots, so I go back to my starting side and I add that second dot. So thinking about phosphorus as having 4 sides, 3 of the sides have 1 dot, one side has 2 dots. That's how you can make dot notation. It's actually, as you learn more about chemical bonding, you find out how very helpful this notation really is. So practice. Hydrogen. Hydrogen's in column 1, 1 dot. That's it. Carbon. Look up carbon's position on the periodic table. It's in column number 4. That means 4 dots. So I put 1 on one side, switch to the second side, switch to a third side, switch to a fourth side, and that's it. That's all the dots I need. Nitrogen. Nitrogen's in column 5, kind of like phosphorus that we just did. One dot on one side, switch to a second side, switch to a third side, switch to a fourth side. That gives me 4 dots, but I still need one more, so I go back to the original side and double up. There's nitrogen. Oxygen, column 6. Write the symbol for oxygen. 1 on one side, 2, third side, fourth side. Still need 2 more, so I'll go back to that original side, go over to the left-hand side, and now I have my 6 dots. 2 on 2 sides, 1 on the other 2 sides. You probably notice that I always have a pattern. I go right, left, top, bottom, right, left, top, bottom. You don't have to do that, but it's a kind of a good habit to get into. Keeps you from putting dots in the wrong spot. Fluorine, one last example here. Fluorine is in column 7. So I go one side, second side, third side, fourth side. Steps to start doubling up now. Dot 5, dot 6, dot 7. And that leaves one open spot here. Fluorine doesn't have a full 8 dots. Now the objective of all atoms when they form bonds and become part of compounds is to become more stable than they originally were. And it turns out that the most stable of all the elements are the noble gases. We can get a clue from this chart that you guys may already have made in a lab exercise. This is a chart that has atomic number on the x-axis, and on the y-axis it's got something that we call ionization energy. Ionization energy is the amount of energy it takes to remove an electron from an atom. If that energy is high, it means it takes lots of energy to break up the atom. That means, in other words, that that atom is stable. Now, if you look at the atomic numbers for the things that are the most stable in any particular group, you'll find that they are, here's element number 2, that's helium. 3, 4, 5, 6, 7, 8, 9. Element number 10, that's neon. 11, 12, 13, 14, 15, 16, 17. Element number 18, that's argon. So you can probably predict what the rest of these spikes are. They're the noble gases. So here's krypton, here's xenon, and there's radon. Well, noble gases have the biggest energy required to break them up, so that means they're the most stable. Elements become stable if they're not noble gases by gaining the same valence electron structure as noble gases have. They want to become like noble gases in their valence electron structure. So that means they want to have 8 dots for almost everything. Now there's one notable exception to that, and that is helium, or things that are closest to helium. In covalent bonding, here's how this works. Stability is achieved through the sharing of valence electrons with another atom. So the valence electrons that an atom has, they're probably not going to be enough. 8 dots for most things is going to be what's stable. 2 dots for hydrogen. You can achieve that through sharing. Here's a great example, water, H2O. If we look at this oxygen molecule here, or oxygen atom here, this oxygen has 6 dots, and it's got 2 holes here, 2 places where there could be a dot. And in fact, to have a full 8, which would be stable for oxygen, it would need to gain 2 electrons from somewhere. Also in water is hydrogen, 2 hydrogen atoms. Each hydrogen atom needs to have 2 dots, because that's what helium has, and that's stable. So it's got 1 dot, but it needs a second dot. Well, here's how this can be accomplished by sharing. If oxygen and this hydrogen atom share that pair, they can both have the sense of ownership of that share that gives them some stability. Here's another place where that could happen. The valence electron from the second hydrogen atom could be shared in that second site that needs another electron. And so when they move in close proximity to each other, close enough to each other that they can share those electrons, they achieve stability. Watch this. With the atoms arranged in this way, we now have some stability. The oxygen is stable because it's surrounded by a full octet, a full 8 electrons. And that's stable for almost all elements. Each of the hydrogens is stable because it has a full duet, a pair of electrons. This hydrogen looks like it owns a pair of electrons. This hydrogen also looks like it owns a pair of electrons, and that's stable because that's what helium has, and that's the closest noble gas to hydrogen. The attraction that each atom has for the shared pair of electrons is what we call a covalent bond, and this stick here represents that bond, that shared pair, is like an attachment stick that holds these two together. The atoms aren't attracted to each other in covalent bonding. They're attracted to a pair of electrons that they both want for stability. It's a lot like if you and your sister both have a car, your parents have given you a car, but the stipulation is you have to use the car together. Even if you don't like your sister, you find yourself spending a lot of time with your sister. Not because you want to be with your sister, but because you want the car, and you have to be with her to get it. This new type of basic particle that's formed when these covalent bonds occur is called a molecule. So this thing right here, that is what a molecule is. It's a covalently bonded little cluster of atoms. Covalent bonding always involves atoms that need to gain more electrons. And the atoms that need to gain more electrons to become stable always turn out to be on this side of the periodic table. If you think about a group 4 like carbon, it needs to gain 4 dots. A group 5 like nitrogen needs to gain 3 dots to become stable. A group 6 like oxygen needs to gain 2 dots to become stable. A group 7 like fluorine needs to gain 1 dot to become stable. All of these things need to gain dots, and so they're going to share with other things to gain those dots. There's another way that they can become stable too. We'll talk about that later on. But for now, we see that these non-metals are the things that do covalent bonding. Now, the noble gases, like let's say neon, for example, they already are stable. They've got a full 8 electrons, a full octet. They're not going to do anything. They're unlikely to bond with anything else. There's a rule that governs all of chemical bonding, except with a few notable exceptions, and that is the octet rule, it's called. An octet is a group of 8. The octet rule says in chemical bonding, atoms will gain full octets in one of 3 ways. One thing they can do is they can gain electrons. They'll do it by gaining electrons. E minus, remember, is a symbol for an electron. Sometimes they'll lose electrons. This process happens in ionic bonding, which we haven't discussed yet. But what we've seen now is that a third way is that they can gain stability by sharing electrons. There are a few exceptions to the octet rule that we have to worry about, and they all have to do with helium. Every one of them has helium as its closest noble gas. Helium only has a full duet, 2 electrons. You think about helium, that's its Lewis dot notation. It's stable with only 2 dots. And so the things that are exceptions to the rule are the ones that are closest, the elements that are closest to helium. Hydrogen is the most common example. Hydrogen is stable with only 2 electrons. So if hydrogen makes a bond, it's stable. Another one is boron. Boron has 3 valence electrons because it's in column 3, and it can't actually support a full octet. It's not a big enough atom. It doesn't have enough holding power. Its nucleus doesn't have enough positive charge. And so a sextet of electrons, which is a group of 6, is sufficient for boron. So you'll see boron making 3 bonds. That's an exception to the rule. And then a third exception is beryllium. Beryllium has 2 valence electrons, and again, it's not big enough to support a full octet. Its nucleus can only really keep 4 electrons around it. So this requires a full quartet. So beryllium stable with 4 electrons, boron stable with 6 electrons, and hydrogen stable with 2 electrons. Here are some other examples. This is methanol. It's an alcohol. CH3OH is its formula. Look at what would have to happen for stability. Carbon needs to share with 4 other atoms to gain its 4 electrons. It has to have an electron there, 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 and there to be stable. These 3 hydrogens each need to share with an atom to gain an electron. This oxygen needs to share with 2 atoms, and this hydrogen needs to share with 1 atom. So here's the combination that could work. If this H and this H and this H all bond with this carbon, all share electrons with that carbon, and this oxygen shares electrons with the carbon and the H, well, you'd have stability in this molecule. Watch. That sharing pattern brings stability. Here's another example, ammonia. Each of these hydrogens needs to gain an electron by sharing. This nitrogen needs to gain 3 electrons, there, there, and there, by sharing. Here's how that could happen. Everything's stable. Full octet on nitrogen, full duet on hydrogen. chlorine gas. It's just two atoms that make a molecule. This chlorine needs an electron, so does this one. So that's how the sharing takes place. Or two hydrogens. Hydrogen needs to gain an electron through sharing, and so does the other hydrogen. So they make that molecule. The last two examples that we saw, hydrogen and chlorine, H2 and Cl2, these are examples of what we call diatomic elements. Diatomic really means two atomed, because the word part di means two. So these two atomed elements travel in pairs, and they form a diatomic molecule by bonding together. Now, if they're combined with other elements in a compound, like if hydrogen is together with chlorine itself, well, then we're just going to get H and Cl. We don't have to have a 2. That's not necessary if it's part of a compound. But when they're by themselves, they are diatomic. They're easy to remember. Here's how you can do it. Go to element number 7 on the periodic table, which is nitrogen. And that's your starting point. Then make the shape of a 7. That gives you 6 of the 7 diatomic elements. So start at 7, make a 7. There's 7 of them. So you need another one, and the 7th one is hydrogen. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen are the 7 diatomic elements.